Okay, we are continuing with the Further Maths chapter summaries. This is Core Pure Year 1, Chapter 6, Matrices. And I say this in every video, it is not possible for these chapter summaries to cover all of the possible ways that examiners can assess the topic. So please make sure you are looking at lots of exam questions. And this is going to be a relatively long video. So I'm going to presume that you've looked through the whole playlist, you know matrices. This is really here just as a quick bit of revision for you. So let's start off with 2x2 matrices and generally just matrix multiplication. Matrix multiplication is only possible for certain dimensions of matrices. So this first one that we've got here, which is a 2x3 by a 2x3, because there is a 3 and a 2 in this middle section, this is not going to be possible for matrix multiplication. But a 2x3 by a 3x2, because they have those matching 3's in the middle, this would be possible in terms of matrix multiplication, and it ends up producing a 2x2 matrix. Matrix multiplication is non-commutative. Normal multiplication is commutative, meaning 3 times 5 is the same as 5 times 3. The order doesn't matter. But for matrices, the order does matter. When you multiply by the identity matrix, you just get the original matrix. The identity matrix I, the 1, 0, 0, 1 matrix, doesn't matter how you multiply it, whether it's on the right or the left, you end up with the original matrix. For a 2x2 matrix, ABCD, if you want to find the determinant of this, you do this diagonal multiplied minus this diagonal multiplied. We'll find out a bit more about what the determinant means in the next chapter in linear transformations. And again, with inverses as well, we'll be able to apply that a little bit more in the next chapter too. So, an inverse matrix, you do 1 divided by the determinant of the matrix. You then swap these elements over, A and D goes to DA. And you just negate these elements. So instead of it being B and C, you get minus B and minus C. Negatives go to positives, positives go to negatives. And this is pretty self-explanatory, but if a matrix is self-inverse, then we can say that the matrix is equal to its inverse, okay? So let's have a look at these 2x2 matrices. Of course, you could do them on a calculator, but I'm just going to be demonstrating to you in this video just how we do matrix multiplication. So AB is 2, 3, 4, minus 1, and we're going to multiply that by 0, 2, minus 1, and 1. Now, if I want to find the top left, it makes sense you're doing the top and the left. The 2 and the 0 multiplies to 0, and the 3 and the minus 1 multiplies to minus 3. Top right, you do the top and the right. The 2 times the 2 is a 4, the 3 times the 1 is a 3, and the 4 plus the 3 is a 7. Bottom left, I'll do the bottom and the left. 4 and the 0 is a 0, minus 1 and minus 1 multiplies to positive 1. And then bottom right, I'll be doing the bottom and the right. The 4 times the 2 is the 8, minus 1 and 1 is going to be minus 1, 8 minus 1 is 7. Now I'm going to demonstrate to you that if we do it the other way around, we do B multiplied by A, 0, 2, minus 1, 1, multiplied by 2, 3, 4, minus 1, will give us something different. I'm not going to go quite as slow as I did in the previous example. So for the top left, I'm going to be doing the 0 times the 2 and the 2 times the 4, which is the 8. The top right is the 0 times the 3, which is 0, and a 2 times minus 1, which is minus 2. Bottom left, I have a 2 and a minus 1, that's minus 2, and a 1 and a 4, which is a 4. Minus 2 plus 4 is 2. And for the last one, the 1 and the minus 3 multiplies to minus 3. The 1 and the minus 1 multiplies to minus 1. Minus 3 and minus 1 is minus 4. And clearly we can see that AB is not equal to BA here, okay? We're now going to find the determinant of BA. Well, we've already worked it out, so we're just going to find the determinant of this matrix. The determinant of BA, that is this diagonal, minus 32, minus this diagonal. So that's minus 32 minus 2 times minus 2 is minus 4. That's minus 32 plus 4 in this question, which is 28 that we have here, okay? So for part D of the question, we're then going to try and find out what the inverse is, okay? So we're going to find the inverse of this. So we already have the determinant. Oh, did I say 28? That's completely wrong. The determinant is actually going to be minus 28. Very silly error to have made there. Okay, so we'll do the inverse of BA. Needs to have the brackets to make it clear it's not the inverse of A, but it's the inverse of them together. It is 1 over the determinant with that negative. We are then going to swap the elements and negate the elements. So when I swap them, when I negate them, I'll get a minus 2 and a 2 that looks like this. And we can just leave it written in this form that we've got here. Okay, so the last part that I've got on this page, it says, given that QPQ equals P, show that Q is equal to the inverse of P. And I've really included this to kind of remind us about how we can do multiplication with matrices on the left and on the right. So the thing we're aiming for is to have Q by itself, and at the moment it's got a P in front and a P behind here. It's kind of worth noting down that if we ever do something like P multiplied by its own inverse, we get the identity matrix, and that's the same thing as doing P inverse multiplied by P. Hopefully that just makes natural sense. When you multiply something by its inverse, you go back to the identity. So I'm going to start off with trying to get Q by itself. If I multiply P inverse at the front, I'll have to do the same on this side like this. So I've multiplied this extra P inverse at the front, here and here. Now the P times P inverse, we've just said, gives us the identity, but effectively what's happening here is they're kind of cancelling out, okay? So we get left with QP on the left, and P inverse times by P is just the identity. Now to get the Q by itself here, I'm going to multiply by P inverse on the right-hand side. So there it is on the right-hand side. I will have to do it on the right-hand side here. Again, those P and P inverse on the left kind of cancel out. And when you multiply anything by the identity matrix, you just get that anything that we had to start with. So if PQP is equal to P, then Q is equal to P inverse. Okay, we are now going to have a look at some stuff to do with 3 by 3 matrices that we have here, okay? The first thing we're going to remind ourselves of is how we find the determinant of a 3 by 3 matrix. Now, I would never use this as like a memory tool, but I kind of will use it to describe how we do this process. So we have this thing like this. The first thing that we do is we take the top value, A here, and then you multiply it by the determinant of the remaining kind of section. So when you have A, you kind of ignore the row and the column that it's in, and you zoom in on that section. You're going to do a similar thing for the middle part, but you're going to do it with a subtract. So for the middle part, we're looking at B. We're then going to ignore that part, and we will do the determinant of the green bit that I've got there, okay? And then for the last part, it goes back to being positive. So for C that we have, we will do C, and we will get rid of the row and column that it's in, and we will find the determinant of the D, E, G, H, the remaining section that we've got there. The main thing that people forget with this, it's very, very easy to forget, is that there is going to be a negative with the B part that we've got there. There are other ways finding the determinant of a 3 by 3 matrix. This is just the most common way that people go about this. Now, to kind of talk a bit about some of the language, when we talk about a matrix having an inverse, we say that it is non-singular. The determinant is not equal to 0. And if it's singular, the matrix has no inverse, and the determinant is equal to 0. And I think one of the ways I remember this is if you have the determinant is 0, you're dividing by 0. That can't exist. So the inverse cannot exist if the determinant is equal to 0. In other words, it's singular. Now, the process of finding a 3 by 3 matrix is actually pretty long. The way that we do this, took a big deep breath here, is we start off by forming the matrix of minors. It has a similar process to this. I'll show you that in an example. You form the matrix of cofactors. This is where, I'm going to draw this out, you negate some of them. It goes plus, minus, plus, minus, plus, minus, makes this a nice pattern like this. Anywhere there's a negative, those terms get negated. You then write the transpose. This is where anything that's going as a row gets transferred to something being as a column. And then you finish off by doing 1 divided by the determinant multiplied by that final matrix that you have got there. But again, this will make a lot more sense in the context of an example. So we have this first matrix that we've got here, this C matrix, and it says, given that C is non-singular, find the possible values of K. Non-singular means we need to do something to do with its determinant. So for part A of the question, I'm going to find the determinant. I'll start off with this 1, and then I'm going to do 1 multiplied by, let's just say what I'm doing here, the determinant of C. It's 1 multiplied by the determinant of this little part. So that's going to be minus 12, minus 4, minus 12, minus 4. And then for the next part of the question, we're going to be focusing on the K part. Remember, it goes with the minus for this. And we're going to be doing the matrix, we're going to do the determinant of this little section. So that's an 8 minus 0. That's 8 minus 0. I'm not even going to bother writing the 0. And then for the last part, well, we have a 0, and it's going to get multiplied by the determinant of this thing, but if we're going to be multiplying anything by 0, it's going to completely disappear anyway, so not that bothered about finding that final part of the determinant. So the determinant is minus 16 multiplied by 1, minus 8k. And if it is non-singular, non-singular means that minus 16 minus 8k cannot be equal to 0. So we just kind of solve this like a normal equation, really. Minus 8k is equal to 16, so k, or not equal to 16, so k cannot be equal to minus 2. If k is any other value than minus 2, then the matrix is non-singular. Okay, part B of the question is the very long process of finding the inverse. So we will begin by doing the first bullet point, which is to form the matrix of minors. When you form a matrix of minors, it's really similar to the determinant process. You concentrate on that one that we're going to do it for, you get rid of these, and you find the determinant of this section. So the matrix of minors will look like this. The 1 is going to be replaced with the minus 12 minus 4, which is minus 16. The k part that we've got here is going to be replaced by the 2 times the 4 minus the 0. So it's just going to be replaced by an 8. I'm going to now just do the rest without all of that kind of highlighting. So for the 0, it is going to be the 2 minus 0. And then for the 2 that we have here, it is going to be a 4k minus a 0. The minus 3 that's in the middle, there's going to be a 4 times 1 minus a 0. The 4 that's on the right, that's going to be a 1 minus a 0. Then the 0 that's in the bottom left is going to be a 4k minus 0. The 1 that's on the bottom is just going to be a 4 minus a 0 that we've got. And then for the last 4 in the corner, we have a minus 3 and a minus 2k, one that's a little bit more complicated for that part. So we've done the minors. We're now going to do the matrix of cofactors. So the ones that need to get changed into being negated are this, 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 and this. In other words, that one, that one, that one, and that one. The rest are all going to stay the same. So for the cofactors matrix, it is going to be minus 16. In fact, I'll change the ones first so I can just concentrate on them. It'll be a minus 8, a minus 4k, a minus 4, and a minus 1. And I'll just fill in the gaps with all of the normal ones that we have there. Okay, and then we are going to do the transpose. In fact, I'm probably going to go straight in with the final inverse. So I'll do the transpose. That is where I said a row becomes a column. First row becomes first column. That's minus 16, minus 8, and 2. Second row becomes the second column. Third row becomes the third column. And to save a bit of time, I've written the transpose at the beginning. I will just do 1 divided by the determinant. And the determinant we worked out was minus 16 minus 8k. Minus 16 minus 8k. And this is what C inverse is equal to. Okay, pretty nasty looking. If this was a number, you could just have it as a 1-mark question in the exam. If it was a number, I would literally just put it in the calculator. As soon as there is an algebraic term, you have to go through this much longer process like this. And at the end of studying matrices, this probably doesn't feel quite as hard as it did at the very beginning. Okay, we're now going to get onto some kind of applications of these kinds of things that we have here. So you can use matrices to form a system of equations. And what you do is you form 3 equations, set it up in matrix form. They're often quite specific about it wanting to be in matrix form, even though it could be done in another way. And then what you end up doing is you just use your calculator to solve these equations. So it says, I am thinking of 3 numbers. Okay, let's call these numbers x, y, and z. The sum of my numbers is 44. Right, so I'm going to form 3 equations. Let's actually start that one then. The sum of my numbers is 44. Okay. The largest number, let's call the largest number x, and I'm going to call z the smallest. So the largest number is 54 greater than the smallest number. The largest number is the smallest number plus 54. Now to get them in that standard form, I want it to be with like the x, the y's, and the z's all on one side. So it's just going to be x minus z equals 54. I'll write it over here, x minus z equals 54. And then the last one says that the largest number is 3 times the sum of the other numbers. Well, the other numbers is y plus z. If I times them by 3, I've then come up with another equation. So x is 3y plus 3z. So that's x minus 3y minus 3z is equal to 0. I'm then going to put that over here. So it's x minus 3y minus 3z is equal to 0. Now, it's very specific. I could just put these in the calculator and solve them, right? I could just solve them straight away like this. However, I am now going to do it in a slightly different kind of way, where I'm going to set it up using a matrix equation. So let's block this off. You can see that the coefficients would be a 1, a 1, and a 1, a 1, a 0, and a minus 1, a 1, a minus 3, and a minus 3 like this. And this is all getting multiplied by x, y, z. If you multiplied that out, you would get everything on the left-hand side there. And this gives us the 44, the 54, and the 0. So if I want to find out what x, y, z is equal to, my three numbers, I can apply the matrix inverse to the left. I can apply the matrix inverse to the left, and then I can just calculate it and see what we get. So I'm not going to actually calculate the inverse. I'm literally just going to write it down like this. 1, 1, 1, 1, 0, minus 1, 1, minus 3, minus 3. I'll just write it like this with the inverse, and I'll put 44, 54, and 0. Now, if you want to, you could go about typing this into your calculator, but I think that's quite a long process. I actually think the simultaneous equation solver, this is quicker. The examiner's going to have no idea whether you've typed it in like this or like this. So I'm probably just going to use my calculator and figure out what x, y, and z are just by typing them in. So I'll go into my simultaneous equation solver. I'll go to three unknowns, and I'll put in the coefficients are the 1, the 1, and the 44. And then I'm also going to put in the 1, the 0, the minus 1, and the 54, the 1, the minus 3, the minus 3, and the 0. And then I'm going to press equals for this, and I get that my solutions are that x is 33, y is 32, and z is minus 21. Let's actually check that these things do make sense, right? In the context of this question, if I add them, they should be 44. So 33... 32 minus 21, yeah, that's 44. The largest number, 33, is 54 greater than the smallest number. 54 plus negative 21 is 33, that's great. And the largest number, 33, is 3 times the sum of the others. 32 minus 21 is 11, times it by 3, and we do get this. So this is definitely correct. But this is what they're looking for that evidence of how to solve a matrix equation here. They do love these questions in the next section I've got here, where it's to do with a system of equations that are representing a plane. So let's look at these three main scenarios where we have some representations of planes here. There are three main ones and a couple of other ones that it could potentially be, but it's very, very rare for them to ask about. First of all, the three planes could intersect at a single point. This is any scenario where the determinant is not equal to 0. If the determinant is equal to 0, we're looking at something different, okay? If they intersect along a line, the determinant is 0 and the equations are consistent. If they intersect along a line, that actually means there is a solution. If they form a prism, the determinant is 0 but the equations are inconsistent. There is not a solution that would work for all of them. There's no place where it would work for all of them. There are some other potential scenarios. The planes could be identical. In other words, they could be multiples of each other. For example, if you had x plus y plus z, let's do it slightly differently, x plus y plus 2z equals 5. If I had another plane that was 2x plus 2y plus 4z equals 10, these are literally the same plane as each other. They are completely multiples. There could be a scenario where they're parallel. So instead of it being equal to 10, it might have been equal to 15. This is where only the coefficients of the x, the y's, and the z's are multiples. The right-hand side is not a multiple, so they're actually representing parallel planes that we've got there. But in general, it's either single point, line, or prism. And I'll talk about this idea of consistent and inconsistent in this next box. So for a consistency check, what you do is you eliminate x, y, or z from two pairs of equations that we have. If they are consistent, then they are identical, or they can be made to look identical. And if they are inconsistent, then the right-hand side is different, kind of like what I was just demonstrating with this part up here. Okay, the following set of equations represent three planes. We've got this, this, and this, noting that there is an unknown value here for p. Determine the value of p such that the three planes intersect in a straight line. So they don't intersect at a single point, they are intersecting along a line, meaning that they do actually have a solution, but there's an infinite number of solutions along that line. Now I've said here, note that the inverse of this matrix, I didn't mean the inverse of this matrix. I'm going to change this in the notes for this, okay? It shouldn't say the inverse. It should say the determinant, so I will change that in the notes afterwards. If you were to calculate the determinant of this, it is actually 0 that we've got, okay? That's because we are referring to this kind of thing that we've got here. And obviously this matrix is corresponding to the values that we have on the left-hand side. So we're going to do a consistency check. We want to make sure that they are consistent because they intersect in a straight line. So the way we're going to do this, if I call this equation 1, equation 2, and equation 3, you just need to use 2 pairs. I'm probably going to do pair number 1 and number 2, and then number 1 and number 3. If you want, you could do 1 and 2, 2 and 3. As long as you're using all 3 of the equations across it, you will end up with the same result. So I'm going to start with number 1, which is 2x minus 3y plus z equals 4, and I'm going to do number 2. I'm going to double it because I'm going to choose to eliminate x. So it's 2x minus 4y minus 2z equals 2p. And eliminate is just like in GCSE simultaneous equations. I'm going to subtract them, so I'll do 1, take away the bottom one. So 2x minus 2x goes, minus 3y minus 4y, that's minus 3y plus 4y, and z minus 2z. Is 3z, and 4 minus 2p is on the right hand side. I'll do number 1, and I'm going to do number 3 multiplied by 2. So there's my 2x, my 3y, and my plus z equals 4. I get my 2x, my minus 2y, and my plus 4z equals 2. So I'm going to subtract them because I must eliminate the same variable. I've always got to eliminate the x's, okay? 2x minus 2x goes, minus 3y minus 2y is minus y, z minus 4z is minus 3z, and 4 minus 2 is 2. Now, for them to be consistent, they need to be identical. Now, they're almost identical, right? Here, this one's been multiplied by minus 1, like this part. Sometimes it might be multiplied by minus 2, or just 4, or 3. But we can make them look the same. So what I'm going to do is I'm going to multiply this whole equation here by minus 1. So that I get y plus 3z is equal to minus 2. Now that I want them to be consistent, I want this one and this one to be consistent. The only way I can make them consistent is if the right-hand side is equal to each other. Remember, if they're inconsistent, the right-hand side would be different. So this means that 4 minus 2p must be equal to minus 2. I will add the 2 onto the left-hand side and the 2p to the right-hand side. So p is equal to 3. Now, if you wanted to check this, if you have a graphics calculator, you could go to your simultaneous equation solver. You could put in all of this stuff here with p as 3, and you should get an infinite number of solutions because intersecting along a line has an infinite number of solutions. If you change this to any value other than 3, maybe 2.999, you will get no solutions on the calculator because the right-hand side of these equations would no longer be identical. They would be different, which means they're inconsistent, which means it forms a prism with no solutions. Okay, we're doing pretty good. We've got one last question to have a look at here, which is the dastardly population modelling that we've got with matrices. The only thing I've really written here is that matrices can be used to model populations. When you multiply by the matrix, what it does is it advances the state to the next day, the week, or the stage. The multiplying by the matrix is like, okay, what's going to happen to these populations next month, next year, tomorrow? If you want to go back to a previous day, you just need to multiply by the inverse of the matrix. Kind of makes sense, right? Inverse is like reversing a process that we've got here. And I think the challenge in these questions is really just there's a lot of text and a lot of trying to understand what is going on here. So, a virus is infecting a population of animals. When first infected, the animal shows mild symptoms and is contagious. After a period, some may develop more extreme symptoms but are then no longer contagious. They then either make a full recovery or die. M with a little n represents the number of contagious animals with mild symptoms. That's why I've picked the letter M on day n. En represents the number of non-contagious animals with extreme symptoms on day n. A model for the population is given by this matrix equation here, where we have an n plus 1 to represent on like the next day, and an n to represent on the current day. So if you want to find what the populations of the animals will look like, you take the previous population and you multiply it by this matrix, where a is an unknown value. On the first day, only animals with mild symptoms were observed. On the third day, there were 72 animals with mild symptoms and 76 animals with extreme symptoms. Find the number of animals with mild symptoms on the first day and the value of A. So, we kind of want to go back from the one we've got more information, which is the third day. We want to go back to the first day, which might be about doing something to do with the inverse. However, they've told us something that makes me think we might be able to go from day 1 to day 3 just by applying the normal matrix. They've told me that there are only animals with mild symptoms being observed. So this means on the first day, we're going to say that there is some number of animals that have got mild symptoms. On the first day, there are no animals with extreme symptoms. And I want to go right through to the third day. So I'm going to take this matrix and I'm going to apply it to these sort of initial conditions. I'm going to apply it twice to find out where I end up. Okay, let's see what happens with this. So I'm going to find out on the second day, this is M2 and E2. I'm going to apply the matrix 1.20, 0.8a. I will apply it to there being K. I don't know how many there are on that first day with mild symptoms, and 0. None of them had extreme symptoms. So we'll do a bit of matrix multiplication. That's the 1.2 times the K and the 0. And then we have the 0.8 times the K, and then we have the 0. So if I now want to find out what it will be like on the third day, my M3 and my E3, I can apply the matrix 1.20, 0.8 and A. I can apply it to how many there were on the second day, which is 1.2k and 0.8k, and I can multiply this out. So 1.2 times 1.2k, that's 1.44k, and then you get a 0 for the next part. And then I'm going to have 0.8 times 1.2k, 0.8 times 1.2, that's 0.96k. You could do it on your calculator, but I know my 12 times table then. And then for the next part, I will have the 0.8k times by the A. So there's going to be a plus 0.8ka or ak, whichever way we do this. So I did this times by this, and then I did this times by this. And we know something, right? We know that on the third day, there were 72 animals with mild symptoms. So for M3, we know that there are 72 animals, which is the same as 1.44k. So I can solve this equation. I can do 72 divided by 1.44, and that will tell me what the value of k is. 72 divided by 1.44 is 50. So this means that there were 50 on the first day. I'm going to continue with the bottom part of this because I know with extreme symptoms, there were 76 animals, and that is represented, if I make this even more clear, that is represented by the bottom element of this. So this must represent the 76. That's 0.96k plus 0.8ka. So 76 is 0.96 times by 50. We just worked out that k was 50, plus 0.8 times 50 times a. So 76 is 0.96 times 50. If I can type properly, that is 48. And then 0.8 times 50, that's just 40. So I'll do 76 minus 48 is 28. And I'll do 28 divided by 40. And I get 28 divided by 40, that's 0.7. So A is equal to 0.7. Let's check we've answered the question. It said find the number of animals with mild symptoms on the first day and the value of A. So I will say here there are 50 animals with mild symptoms on the first day. Okay. It then says scientists want to refine the model after further observation. Suggest which element in the matrix should be increased if they believe that contagious animals are spreading the virus quicker than the model predicted. Okay, this is where I actually think writing out the equations can be really helpful for this. So I'm just going to quickly think about what this is representing. Okay, I'm going to write this down here that we have the mn plus 1 and the en plus 1. We are multiplying it by 1.20, 0.8. We calculated that A was 0.7, and this is mn and en. So if I was to actually multiply this, you get 1.2 mn, and you get the 0 part. You then get 0.8 mn plus 0.7 en. I've made a bit of a mess of that. Let me just tidy that. Plus 0.7 en. And this is what mn plus 1 and en plus 1 is equal to. In other words, to find out the number that are have the mild, you just take the previous number of mild and you multiply it by 1.2. So it's saying that they're the contagious ones. You find out how many of them had the disease, and the next day there'll be 20% more of them with the disease. So actually I think that's going to be the variable we're going to want to change. If we want to make the contagious animals spread the virus quicker, then instead of them just spreading it 20% more, I think we would want to increase the 1.2. So for part 1, we would want to increase the 1.2 element. And then for part 2 of the question, it says, what would the scientists need to do? Which element would they need to increase if they believe that some animals with extreme symptoms are also contagious? So let's just quickly look at what this means. This is saying that the extreme symptom ones, it's saying that 80% of the previous day's mild symptoms are converting to extreme symptoms. Some of them aren't converting. And it's also saying that 70% of them with extreme symptoms are still there. That other 30%, they may recover or they may die. But if we think that these are somehow going to be, these extreme ones are actually contagious, I think we need to change this 0, because then we would have that the ones who are getting mild symptoms is related to the number of extreme ones that there are. Previously, the extreme ones had no impact on that because they weren't contagious, but the scientist is starting to think they might also be contagious. So we need to increase the 0 that we have there. So we would want to increase the 0 element. So maybe this part here of kind of like writing it out so you can clearly see what each thing is equal to, even like this kind of way, takes it away from being about matrices and actually just takes it into equations where we can try and think a little bit more sensibly about how these things might be working. There are some very tough exam questions on these ones where you do need to use the inverse, but like I said, I can't cover absolutely everything in this. So that's everything I wanted to talk to you about with matrices. Obviously, it comes up again in some stuff to do with linear transformations. If you are interested in applying for a scholarship where you can win £150 and potentially a graphics calculator, this is a yearly scholarship that I run. It is currently live at the time this video is published, but it should be happening year on year, usually in like the autumn term. So if you're interested in that, you can just search up the Bison Maths Award and hopefully you might see if you can apply for it. Wishing you the best of luck with all of your studies, and I hope to see you in another video sometime soon.